Hello everyone, this is Dr. Zach. Today we are going to evaluate improper integrals. Go ahead, take a look at question A in your lesson preview. Write out all your work, use the correct notation. Notice for this volume problem, you were rotating about the x-axis. You want to use dx when you write your integral. The endpoints are going from 1 to infinity. This is called an improper integral. And hopefully you used limits in order to set up your problem. When you write your problem, keep your pi, write the limit. Let's use b goes to infinity for your integral from 1 to b 1 over x squared, or we'll write x to the negative 2 dx. After that, make certain that you integrate. Use your equal signs appropriately, and we will have the limit as b goes to infinity of our negative 1 over x squared, evaluated from 1 to b. We still haven't substituted, so keep using your limit notation until we have substituted the b in through our limit, and then we will have minus a negative, which is plus 1. Now, as you evaluate your limit, you notice that 1 over b is going to 0, and you end up with pi. So the volume of Gabriel's horn as it goes to infinity is pi. So this is a finite value, even though the surface area of this problem is infinite. So when we write a definite integral, we're required to have limits of integration. That would be a and b. They must be finite. In order for a fundamental theorem of calculus to work, we have to be continuous on that interval ab. But improper integrals are ones that may not be continuous on ab, or they're integrals that may not have finite endpoints. So an improper integral is said to converge when you have a finite solution, or that the integral exists, whereas an improper integral is said to diverge when your solution goes to plus or minus infinity. So we're going to work on improper integrals today to determine whether or not they converge to a value or diverge to positive or negative infinity. As we look at our example 1, it's a simple integration problem, and when we integrate, we're going to rewrite our problem using limit notation, the limit as b goes to infinity of our antiderivative negative e to the negative x, and we're going to evaluate from 0 to b. Keep your limit notation until we're ready to use it. We keep the limit, b goes to infinity, negative e to the negative b, then we substitute our 0, and minus minus becomes plus e to the 0. As we evaluate the limit, we notice that we're going to have negative 1 over infinity, which will tend to go to 0. So we have 0 plus 1, and the answer is 1. So because we have a finite answer, this integral is said to converge, and it converges to the value of 1. And when we look at example 2, notice one of the endpoints again is going to infinity. So we know and understand that this is now a limit problem. Keep your limit as your b goes to infinity. And we also know that the antiderivative is the arctan of x for this problem. We're going to evaluate from 0 to b. Substitute, we'll have the limit as b goes to infinity, the arctan of b minus the arctan of 0. All right, now, as the tangent goes to infinity, we know that the angle is going to pi over 2. So when we evaluate b going to infinity, we're left with pi over 2 minus, and the arctan of 0 is 0. So we get, again, a problem that converges, and it converges to the value of pi over 2. Example 3 is set up very similarly. As we evaluate the limit as b goes to positive infinity, we'll get the natural log of infinity. Well, the natural log of infinity tends to go to infinity, and the log of 1 is going to be 0. So this problem is going to infinity, and we know that the antiderivative from 1 to infinity diverges. For example, 4. Looks like we should use integration by parts. The u is 1 minus x, and our dv is going to be equal to our e to the negative x dx, in which case du is negative dx, and v is going to be negative e to the negative x. Put it all together. Don't forget your limit notation. The notation matters. We have b goes to infinity, and we will have u times v, which is 1 minus x, times your negative e to the negative x, minus the integral of negative dx times the negative e to the x. It's negative e, negative x dx. Now, let's work some more. A little bit of algebra. B goes to infinity. The first part is going to be integrated from 1 to b, and let's not forget 1 to b on that second antiderivative, which gives us negative 1 minus b, e to the negative b. Put your 1 in, that gives us 0, minus, we're going to integrate again, which is going to make it positive, e to the negative x, evaluated from 1 to b. A little bit more substitution. Keep your limit notation. We have our b going to infinity, and we'll have a negative e to the negative b plus b e to the negative b plus e to the negative b minus e to the negative 1. As b goes to infinity, a lot of this is going to 0. Let's see here. E to the negative b goes to 0, b e to the negative b goes to 0, e to the negative b goes to 0. We're left with negative 1 over e. Therefore, this example converges, and it converges to the value of negative 1 over e. Oh no, take a look at example 5. Did you notice that the limit is going to positive infinity and negative infinity? Which means we're going to have to break this problem into 2 parts. We're going to first look at the limit as a goes to negative infinity for your integral from a to 0, e to the x over 1 plus e to the, oh look at that, e to the x, and that's going to be squared dx. And then we will add on the limit as b goes to infinity of this problem going 0, notice how they connect, to b e to the x divided by 1 plus e to the x squared dx. Now the reason I wanted you to think of it that way is we should let u equal e to the x, so that our du would be e to the x dx, and that's going to be a very convenient u substitution. All right, so now think first about the limit as a goes to negative infinity. Using your u substitution, we're going to rewrite this as a to 0. Remembering, please, those are x values. We have 1 over 1 plus u squared du. And you know that that is an arctan problem. So we keep the limit as your a goes to negative infinity. We have the arctan of e to the x, and this is going to be evaluated from a to 0. Keep your limit. A goes to negative infinity. We have the arctan e to the 0 minus the arctan of a, e to the a. All right, and when that simplifies, we get the arctan of 1, which is pi over 4. Then we evaluate. Remember, this was going to negative infinity. E to the negative infinity is 0. And the arctan of 0 is also 0. So now we've got that first part done. We need to think about the second part of our problem. But most of the hard work's finished. Let's see. We will think about the limit as b goes to infinity. And this time, we're going to get the arctan of e to the x evaluated from 0 to b. in which case we then have the limit as your b goes to infinity, arctan e to the b minus arctan e to the 0. b goes to infinity, that means the arctan's going to infinity. We are at pi over 2 minus, and then e to the arctan of 1 is equal to pi over 4. Whoop, that's not a 4. Combine your two answers, and you come up with a lovely pi over 2. And we know that this integral, which is improper, converges. Now I'm looking at example 6. I don't see infinity. So if there's no infinity, this is not an improper integral. Yes. Okay, look again. The endpoints you have are going from 0 to 1. If you substitute 0 in for 1 over x, the third root of x, you have 0 in your denominator. That's what makes this an improper integral. So we're going to write the limit as a goes to 0. This has to come from the right side, though. And when you integrate, you should get your 3 halves x to the 2/3, and we're going to evaluate that from a to 1. Follow through. Make certain you keep all the notation. A is going to 0 from the right. Substitute your 1 in. We have 3 halves, and that will be subtracting 3 halves a to the 2/3. Put your 0 in, and you end up with 3 halves. Again, this is an improper integral, and it does have an answer, even though the original problem was dividing by 0. Think again about how amazing that is. As you look at example 7 and 8, notice you once again are dividing by 0 for example 7, whereas example 8 doesn't seem to have any problem. But you've got to recognize that 0 is in between -1 and 2. So you're going to have to divvy this up into 2 problems for example 8. So let's start. We're going to have the limit as a goes to 0 for our first problem. You're going to then write your integral from a to 2 of 1 over x cubed dx. Find that antiderivative and go ahead and solve the problem. For example 8, you have to bust this one into 2 problems, and we're going to write the limit as b goes to 0. We're going to have the integral from -1 to 0, 1 over x to the 3rd dx, plus the limit as a goes to 0, the integral from 0 to 2, 1 over x to the 3rd dx. Go ahead, solve questions 7 and 8. Determine whether or not these integrals diverge or converge. For question 1 and 2, I want you to confirm that question 1 has an answer of pi. And of course, you already know the answer for question 2 is 2 pi, but I want you to use the formula for arc length and find your antiderivative to prove this using integrals. Next, we're looking at our lesson practice. We're going to determine all values of p for which this improper integral converges. So we're trying to generalize some ideas. Question B, we're going to go from 0 to 1 and figure out where they also converge. So start by rewriting the problem using your limit notation. We have the limit as your b goes to infinity of x to the -p plus 1 divided by -p plus 1. And we want to evaluate this from 1 to b. Do your substitution. Keep your limit as your b goes to infinity. We will have b to the -p plus 1 all divided by our -p plus 1. Now, as b goes to infinity, what is happening here? Since b is going to positive infinity, everything's going to depend on what's happening with -p plus 1. If -p plus 1 is less than 0, then the b value goes to your denominator, and it will tend to go to, your answer tends to go to 0. Solve this, we know that if 1 is less than p, or if p is greater than 1, then our integral will be convergent, since we'll be dividing by 0 as b goes to infinity. Now, if negative p plus 1 is greater than or even equal to 0, we're going to be dividing by 0 in your denominator, or we're going to head out to positive infinity in the numerator. So if we solve this, we know that if p is less than or equal to 1, our integral is divergent. So we then know how to just look at some of our functions to see if they are convergent or divergent. So if we were to determine all values of p for which this improper integral converges, think about what happens as your a value approaches 0. So the results from a and b are going to be very useful to us later on in this unit. If we go from 1 to infinity of 1 over x to the p for dx, we know that it's going to converge for p greater than 1 and diverge for p less than or equal to 1. Whereas if we take the integral from 0 to 1, 1 over x to the p dx, you figured out that it's going to converge for your p's less than 1 and diverge for p greater than or equal to 1. And that is going to be useful when we start comparing integrals during our improper integral test. So suppose we have f of x and g of x that are continuous, and we know that g of x is always smaller than f of x on AB. Then if f of x converges, that's going to force g of x to converge as well. Think about that for a minute. F of x is going to a certain value when we look at our area function. G of x is always smaller than f of x, so it's going to be forced to stay underneath that value in terms of area, and it will also converge. Whereas if g of x, which is smaller, diverges and the area heads to positive infinity, and f of x, which is always larger, it's going to stay above g of x on that interval and also go to positive infinity. And that will help us with some problems later on. So for example 9, notice I do not know how to find an integral of e to the negative x, but I do know that the integral from 1 to infinity of e to the negative x dx converges. Using our comparison test, since we know that e to the negative x squared is less than or equal to e to the negative x, then the integral from 1 to infinity of the smaller term, e to the negative x squared dx, must also converge. If we look at example 10, think about a similar function. I don't know, how about the integral of 1 over x to the 5th? Make a comparison to see if that integral converges or diverges to tell you what's happening with 1 over x to the 5th plus 1. Go ahead and give questions 54 through 62 a good try. Have a great day.